Coyote Prosthetics, a Boise-based prosthetics manufacturer, needed an affordable solution for structural testing of prosthetic feet to meet ISO 10328 standards. These standards are vital to ensure the safety and durability of prosthetic devices, protecting against potential injury and litigation. Outsourcing this testing to third-party facilities was cost prohibitive for the company, prompting the development of a custom-built testing machine. This machine incorporates linear actuators to apply static and cyclic loads and uses a microcontroller with Arduino interface to log data on force and cycle count. The design offers a cost-effective in-house solution for testing various prosthetic foot sizes, significantly reducing testing expenses while enhancing operational efficiency.
To ensure durability over 2 million test cycles, we built the frame using welded steel box tubing, designed to withstand high vibrations and loading forces. Our design accommodates various prosthetic foot sizes and testing forces through multiple adjustable components. The mounting rod can be repositioned, the actuator stroke length is adjustable, heel and toe plates have multiple levels of adjustability. Additionally, we designed the frame with extra space to prevent components from being crammed together, allowing for easier maintenance and adjustments. The overall frame dimensions are also within the size limits specified by our sponsor, Coyote Prosthetics.
Our design implements an Arduino Opta PLC that allows analog control of our industrial components and supports feedback from onboard instrumentation such as the electronic pressure regulator and 2 piezoelectric load cells. To maximize the capabilities of an electronically controlled system, we additionally opted to use electronic double-acting solenoids to provide control capabilities to our pneumatic actuators. The selection of these components gives us the greatest flexibility to include data logging, precise control, and test validation throughout the life cycle of the device. The human-machine interface software, Ignition, grants the user the option for complete hands-off automation or more direct hands-on operation of the machine, depending on their preferred testing criteria.
Our main driving components that are able to make our device run consisted of pneumatic actuators, load cells, and an Arduino PLC, with of course additional supporting components. Pneumatic actuators provide forces that are applied to the prosthetic foot via compressed air. Load cells read and send the forces measured back to the PLC. Solenoid valves control the airflow to the pneumatic actuators by using an electrical signal to open or close the air supply, allowing for precise regulation of force application during testing. Air regulator maintains a consistent and adjustable air pressure to the pneumatic actuators, ensuring precise force application for accurate and repeatable prosthetic foot testing.
The Arduino Opta PLC with an analog extension, paired with Ignition for a human-machine interface, creates a powerful and flexible automation solution. This PLC delivers reliable control with digital and analog I/O for seamless integration. When combined with Ignition's web-based HMI, users gain interface monitoring, remote access, and control. This setup ensures efficient data tracking, actuator management, and alarm handling, making it a high-performance solution for industrial automation. When integrating load cell amplifiers into our system, we ensure precise and reliable force measurement, feeding accurate data to our PLC for real-time processing. These amplifiers transfer a millivolt signal generated by the load cells into a voltage that is readable by the PLC. A stable power supply is critical, guaranteeing consistent performance without signal fluctuations. Safety also remains a top priority, which is why we've incorporated an emergency off button. In the event of an unexpected situation, this instantly halts actuation and testing, protecting both the user and surrounding personnel. In the event of our emergency power button being hit, all of our data is saved on both the PLC and Ignition as well. Our system is designed for precision, efficiency, and above all, safety.
To ensure a precise and sturdy frame, we welded steel tubing while maintaining strict tolerances within 0.2 millimeters and 0.2 degrees. We exclusively used machine shop tools like the bandsaw, mill, and MIG welder to achieve accurate angles for the heel and toe actuator supports. CNC milling was used to ensure the holes were precisely drilled in the correct position and depth. The ISO document ensures safety and highlights that the test must conform to high standards, obtaining data within the allowable degrees and measurements set forth by ISO. Accuracy of manufacturing methods were immensely considered. Our actuator supports presented a lot of importance for accuracy of the project. Cutting accurate angles took a few tries. Metal distortion was a major concern that would cause inaccurate dimensions and angles, especially at the actuator supports. To avoid major expansion and contractions, jigs were incorporated within the pre-welding process. Testing assemblies were made to fine-tune welding and fixturing. The final product took a few tries, but our team was persistent and were able to meet ISO 10328 tolerances without requiring more material to be ordered from our sponsor, and scrap was utilized from the machine shop to further avoid additional costs.
We encountered a challenge when integrating our load cells, as we initially struggled to process the 5-wire analog signal properly. The load cells work by generating an electrical signal when placed under mechanical stress. This is done by a quartz crystal that is within the load cells and many alike. The electrical signal generated is too small for our system to recognize. The amplifiers we found give us a plug-and-play solution to read the signal from these load cells.
Now we'll demonstrate the device in action. First, the operator loads the test sample into the device by sliding the collar over the support shaft and tightening the set screws. The operator will then initiate the test cycle via the interface, either utilizing the fully automated controls or via the manual override operation. If automated control is selected, the device will conduct a cyclic test of the sample in compliance with our ISO standard, ISO 10328. You can see here the smooth operation of the pneumatic actuators, fully able to meet the functional requirements of the ISO standard. In the event of device malfunction, part failure, or other catastrophic unplanned events during testing, the operator should use the emergency stop button, or EMO, to immediately cut power to the device, halting the operation of the test and movement of the actuators.
We are incredibly proud of this project and how it brought together everything we've learned in our mechanical engineering education. From structural design and machining to electronics, coding, and pneumatics, this was truly a unique and specialized project, giving us hands-on experience solving real-world engineering challenges. A huge thank you to Coyote Prosthetics for this opportunity. Their support allowed us to develop a machine that will improve their testing capabilities while giving us invaluable experience applying our skills in a meaningful way. This project was the perfect culmination of our time at Boise State.
Then you pop 'em, you can't man 'em, then you mop 'em, you can't stand 'em, then you drop 'em, you pop 'em, 'cause we pop 'em like over red and vodka.